We now introduce total complexes. So total complexes are precursor to spectral sequences. So let us see how these total complexes are built up. So consider this chain complex. So this chain complex, say ending in 0, this lies in column 0, so that's why the first index is 0. And the second index is decreasing 4 to 3 to 2 to 1 to 0. So this is a chain complex, and the differential map is D0. To be more precise, we can write it as D0, 4 because it is coming out from 0, 4. And this is D0, 3 because it is coming out from module 0, 3. So this is D0, 2. This is D0, 1. So we just write D0 if we are clear that this chain complex lies in the 0th column. Now consider another chain complex which lies in the first column. Again it ends at 0, so it goes from 4 to 3 to 2 to 1. The first index denotes that these modules, these are bigraded, they have 2 indices, but this chain complex lies in the first column. So again the map here is D1, but more precisely you can write it as D1, 3. This you can write as D1, 2. Obviously these two match these two. 1, 3 matches 1, 3. And here you have D1, 1. So this 1, 1 matches this. And this is D1, 0. So again we just write it as D1, just like we do in chain complexes. Rather than writing index of the module from which the map is coming out, we just ignore the second part, but it will be clear from the context. So now look, another chain complex living on the second column. So here the differential map or the boundary map is D2. You want to be more precise, you can write this as D2, 2. So this 2, 2 comes from here. This is D2, 1. So look at another chain complex living on the third column. So again we are going from 4 to 3 to 2 to 1 to 0. So here your differentials are D3. Look at another chain complex living in the fourth column. Again you're going from 4 to 3 to 2 to 1 to 0. So again you can write the differentials here as D4. And if you want to be more precise, you can say D4, 3 because this is coming out from this 4, 3. So we have these bunch of chain complexes which live on the columns. So now we will have the same modules, but the chain complexes will be in the rows. So we have already seen vertical maps, and these modules are the same which we had shown in the vertical maps, and now we are looking at horizontal maps. So now look at this chain complex which is sitting on the 0th row. So notice the second coordinate is 0, sitting on the 0th row, and it is going from 4 to 3 to 2 to 1 to 0. So this is a chain complex, and the differential here is delta 0. So this delta 0, more precisely we should write it as a delta 1, 0 here because it is coming from 1, 0. This is coming from delta 2, 0. This is coming from delta 3, 0. This is delta 4, 0 because it's coming out from this map. So we have this chain complex here. Now we can talk about another chain complex which can sit in row 1. So the chain complex which sits in row 1 has these differentials as delta 1. So this differential, more precisely we can write it as delta 1, 1. This is delta 2, 1. This is delta 3, 1, delta 4, 1, and so on. Then you can talk about another chain complex which is horizontal and sits in the second row. Notice the second index is 2, and the map here is delta 2. The differential here is delta 2. If you want to be more precise, you can write this map as delta 3, 2. But from our notation and the way we are writing it, it is clear from where the map is coming out. So if it is horizontal coming out like this, it has to be delta. So you have horizontal complexes like this. So you keep on having horizontal complexes like this. So this will be delta 3, delta 3. You want to be more precise here, you can say delta 4, 3. But if we just write delta 3, we know that this is the differential which is associated with the chain complex which lies in the third row. Now you have another chain complex which lies in the fourth row. another horizontal chain complex. So it's in the fourth row, second index is fixed at 4, and the first index is going from 4 to 3 to 2 to 1 to 0. So you can continue having these chain complexes which will lie horizontally like this. Now let us put both the vertical and the horizontal chain complexes together. Now we put both the vertical and the horizontal chain complexes together. So vertical chain complex is given in orange, as you can see, and the horizontal ones are given in green. So from the vertical chain complex, you get d square is 0. Whether it is d0 square or d1 square or d2 square does not matter. And from the horizontal, you have delta square is 0. Now we might think that this square should commute. So say we are focusing on this square. So you first apply delta and then d. First apply delta and then d. This should be equal to first apply d and then delta. First apply d and then delta. So this is commutativity. But this does not hold in a total complex. And why this is so, we will come to it very soon. So there's a natural reason for it. Instead, what we want is anti-commutativity. That is, we want d delta should be equal to minus delta d, or the way to write it is d delta plus delta d should be 0. And to achieve this, what we essentially do is you keep the first differential d0 as such. This index is 0, so keep it as such. In the first column, because the number 1 is odd, you put negative signs. In the second column, this 2 is even, so you keep it positive. In the third column, you have d3, 3 is odd, so you make d3 as negative. So d4 is even because it's lying in the fourth column, so you keep it as such. So d4 is as such. Now if you do this, so obviously now you have a negative sign here which will come out here, and you will get the anti-commutative condition. So this is called anti-commutative, and this will pop out naturally later on. So we need to keep this in mind. So there are three things. So this is a total complex. You have d square is 0, delta square is 0, and you have an anti-commutative condition like this. Notice that we have a bigraded complex. So every module has bigrading. So as you can say I and j. And we have these maps D which correspond to vertical chain complexes. So these maps D have differential by degree 0 minus 1. So they keep the first as such, so 0 is kept as such, and the second is decreased by minus 1. 4 goes to 3, 3 goes to 2, 2 goes to 1, 1 goes to 0. Or you can see this vertical chain complex first is as such, so first degree is not changed. So 3 minus 0 is 3, 3 minus 0 is 3, fixed at 3. The second one goes down by minus 1. So 4 minus 1 is 3, 3 minus 1 is 2, 2 minus 1 is 1, this. So you have D is of by degree 0 minus 1. So corresponding to vertical chain complexes. And delta corresponds to horizontal chain complexes. So it is minus 1 and 0. So you can just pick up, say, this chain complex, horizontal chain complex. You need to see that the second index is constant, 4, 4, 4, 4, 4. Second index just changes by 0. But the first index decreases by minus 1. So 4 minus 1, 3, 3 minus 1, 2, 2 minus 1, 1, 0. So this is decreasing. And we have D square is 0. So because we have deliberately put vertical chain complexes with D, and delta square is 0 because horizontal chain complexes come from delta. And we talked about this anti-commutativity condition. So this is important, and we will see that this comes naturally later. So this entire thing with these three conditions, D square is 0, delta square is 0, and this anti-commutativity, this is called the total complex, and we denote it as tot of M. And the grading, this is given as this. Tot of the nth piece is I plus j is n, mij. So what does this mean? So let us see it more closely. So what is 0? So 0 is just this module, because sum of these two is 0. So this is just tot of 0. Now what is in 1? So this is tot of 0. So in the first, this is tot of 1. Then because 0 plus 1 is 1, 0 plus 1 is 1. Then what is tot of 2? The second grading, it is just 3. So all these elements which lie on the anti-diagonal. So this is grading 2, tot of 2, because 2 plus 0 is 2, 1 plus 1 is 2, 0 plus 2 is 2. Then what is tot of 3? All these elements which lie again on the diagonal. So this is tot of 3. So direct sum of these. And the differential map, this is just going from tot of 3 to tot of 2 to tot of 1 to tot of 0. So let us see this more descriptively. So this is our total complex, and we have some differential d which we have to talk about. But tot 0 just consists of one piece. Tot of 1 is direct sum of these two modules whose index sum up to 1. Tot of 2 is direct sum of these three modules and their indices sum up to 2. 2 plus 0 is 2, 1 plus 1 is 2, 0 plus 2 is 2. Tot of 3 is these 4. The indices sum up to 3. Tot of 4 has these elements and the indices sum up to 4. 2 plus 2 is 4, 1 plus 3 is 4, and you can see. So this you can think of it as a chain complex, say C0, C1, C2, C3, C4. So this is a chain complex. So obviously we want to compute the homology of this chain complex. And computing the homology of this chain complex is what gives rise to spectral sequences. So we understand now the structure, how these total complexes come about. But to make this a complex, we have to talk about this boundary map or the differential D. So we have to further talk about this differential D. So when we talk about this differential D, we will automatically see that the anti-commutativity condition pops out. So we want to talk about the differential which goes from n to n minus 1. So this differential here is d3, here it is d2 and d1. So let us focus on, say, this portion here. So what is the differential? So differential obviously consists of two things. One is d and one is delta. So obviously this goes to 0 here. So we had appended zeros here before, so we don't have to worry about this map here, and here again it goes to 0. So we are worrying to go from tot of 3 to tot of 2. So from this entire diagonal to this entire diagonal. And what takes us here? Only two maps. Delta will take you here and d takes this to this. So if you're focused on M21, this gets mapped at two places. Via delta it gets mapped to M11. Via d it gets mapped to M20. So you see that the degree here is 3, 2 plus 1 is 3, but here it decreases 0 minus 1, so goes to 2. Here again it decreases minus 1, 0, so goes to 2. So there are only two maps, d and delta, and both act on the module. In fact, on every module we just have two maps. Here again the map is delta, but it is 0. Again delta and d. Here again two maps. Delta is taking you here, the d is taking you to 0. So the two maps obviously corresponding to every module, you have two maps, and those are two maps you take, dij and delta ij, just to specify that this delta and d correspond to the every module from where they come out. Now you compose two d's. To show it as a chain complex, we have to show that d square is 0. So to compose two d's, you have d plus delta and d plus delta like this. So you will get d square, delta square, and then you will get this condition. So this is 0 automatically because we forced this to be a vertical chain complex. This is 0 automatically because we forced this to be a horizontal chain complex. And this is 0 because of our anti-commutativity condition. So this anti-commutativity was very important to make this a complex like this.